Whoosh. All right, so we're on example 6A. We had just finished putting Tate, who is sitting in the Austin airport right now, hoping that his flight to DC is not canceled because they're getting like apocalyptic snow up in that area. We didn't finish. He's not done. He still has to get where he needs to go, and we still have the same to do as well. But we did factor out the least power, right? And just to review that, you're pulling out the exponent that's the smaller number, not the smaller magnitude, but the smaller number. So any negative number is smaller than a positive number, and we're dividing out. So when you do that, you subtract. So you can imagine a horizontal division bar here, and it's what you started with, divided by what you're taking out, and you subtract the exponents, right? And be careful, when you subtract the negative, it becomes positive. Always mentally redistribute just to make sure that you have it correct. And that's the quickest, fastest, most efficient way to get it into that final form. Now, some people kind of don't like doing that. So real quickly, let's look at the other way. From this line here, if you simply put it back into radical form, 10 over 3, this would be k to the 2/3 in the top, and then minus 2 over 3 k to the 1/3 in the bottom. You need to get it back together. You need a common denominator, don't you? So what would be the LCM? Well, they both have a 3 right now, but I would need to multiply the other one by k to the 1/3 times k to the 1/3. One in the top, one in the bottom, because that's equal to 1, right? And then you can get there in an extra step, but you can get there nonetheless. The common denominator is now the cube root of k. And now, because you're multiplying, you add those, right? 2/3 plus 1/3 is 3/3. And you get 10 k to the first minus 2. And then you could factor the 2 out. So it actually would take 2 more lines if you want to factor that out. But that's another way to do it. Put it all back in fraction form, get a common denominator, and combine. But if you can practice, right? Practice on your own, factoring out least powers, it's a nice little time-saving skill. That's like taking your game to the next level, right? I got this, and then pretty soon I'll be on Brody's, like, what you call it? A big kit? Arena kit. I called you Brady or Brody? Braden? Brody. Brady. Brady and Broden. Gotcha. No, I got it. Yeah. So, because I'll be practicing this during my conference period, that's all I'm going to do. You know, proverbially now the Mrs. Lincoln and Mrs. Smith are going to be banging on the doors asking me to keep the noise down. Right? Anyway. What? No. I'm a trumpet player. All right. Cornet player. Sorry. Now what? Now we find the critical values. What's the domain of this function? Way back in the day, we talked about it. All real numbers. Yeah. So the function has no discontinuities, but the derivative obviously does, because now it has a variable in the denominator. So we look at that first. T prime equals dne when the denominator, 3 cubed root of k equals 0. Divide by 3, cube both sides, you get k equals 0. Did we already know about that one? Yeah. Were we on cusp alert for this guy? Yeah, we were. So as we've already seen, that's going to be a value that's in the domain, but the derivative is undefined because it's infinite. So it's going to be one of these types of scenarios, vertical tangent. In 2 of the 4 cases, it'll be a local maximum, and the other 2, it's not. Then we say that t prime or t prime of k equals 0 when the numerator is equal to 0. And then we solve that, divide by 2, add 1, and divide through by 5, we get 1/5. And that's going to be one of these guys. It's going to be like increasing x cubed, decreasing negative x cubed, or one of those. So again, in 2 of the 4 situations, it will be a local max min, and the other 2 it won't. And now we're at the point where we have to determine from the information of the first derivative whether or not they are. And so that's where the number line chart comes in. So now we'll come up here, let's new column. We got k and t prime. What if you don't put k and t prime, you accidentally put x and f prime? Is that okay? It's not bad. If there's only one function that we're talking about and you accidentally call it x and f of x, usually they don't deduct anything. But again, you want to try to have the flexibility to switch variables if you need to. So I have a 0 here and a 1/5 there. And now I pick my test values. So like -1. Let's see. If I pick something between 0 and 1/5, 1/6 wouldn't be bad. But remember, you're going to be multiplying it by 5. So we can handle a 6, but maybe 1/10. Or what? Since Brody spoke first, I'll give him 1/6. Y'all could try 1/10, see if we get the same answer. And something to the right of a 5th? 1. Yeah, there you go. And now here is the full-fledged factored version of t, right? Of t prime. The 2 doesn't affect the answer because it's +2. The 3 doesn't affect the answer because it's +3. The cube root of a positive number is positive, and the cube root of a negative number is negative. So the bottom is determined by k, and the top is linear. So let's plug in a -1. -5 minus 1 is negative. Over the cube root of a negative is negative. What's a negative over a negative? Positive. Plug in a 1/6. 5/6, right? -1 is negative. Or 5/10, which is a half, minus 1 is still negative. So the top is negative, and then the cube root of 1/6 is positive. So we get a negative over positive, which is negative. And if you plug in a 1, you get positive over positive, which is positive. So once again, we do see a sign change every interval, but don't expect that to be the case. So I'm going to forego the listing the intervals of increasing, decreasing. So remember that 0 was the vertical tangent. So increasing to a vertical tangent, decreasing, and then this is going to be horizontal tangent. So it looks something like that. So t has a local max. Now, did it say find the x coordinates only? Okay, good. T has a local max at x equals 0, comma, because t prime changes from 2, right? From positive to negative, period. Or what? At x equals 0. Say it twice, or at that point. And a local min, so you can piggyback on the subject of t, a local min at x equals 1/5, comma, because t prime changes from negative to positive. Not in France, but at x equals 1/5. All right. So that's a lot of writing. So perhaps on a free response question, you're only asked to find the x coordinate where the function has a local max only, right? Or the local min only. Now, if you were interested in sketching the graph, you could actually find the y value at 0, the y value at 1/5, and you could sketch it. I think the y value at 0 is 0, so it actually kind of comes in like this to the origin, does that, and then goes up like that. So just based upon that limited information, we kind of know this about the function. It looks something like that. Vertical tangent, horizontal tangent. Now, I'm not going to work Jenna, not because I don't like her as much, but the only difference really is one of these ends up being, it's the same sign on both sides. So there is not going to be the local min here. I believe it looks like this. It comes up and bounces 0, and then it does this and continues down. So we have a horizontal tangent, but the derivative is negative on both sides. So if we had the time, we would do it. You would work it the same way. Maybe you try it on your own as an extra practice. Since there's not as many on the worksheet, feel free to do that. Okay. But there's only going to be one sign change. So on consecutive intervals, you're going to have the same sign of the derivative. All right. So that's for continuous functions. The first derivative test is a test for what? No, it's a test. Okay, it's a test to find what for continuous functions? Relative extrema. The first derivative test is a test for relative or local extrema for continuous functions at critical values. We already have the critical values in hand. We already have the continuous function in hand. We just analyze. It's really the analysis of the sign change of the first derivative on either side to determine if there's a local maximum in either. Okay. Now, what if the function's not continuous? Then it's just like, I give up, transfer out. No. Well, a graph is worth 1,000 words, I think they say. So if we can sketch the graph, hey, it might tell us the story. So is this function continuous for all real numbers, f of x? This is the next example, by the way. Well, let's see. It's defined everywhere, isn't it? We got a line to the left of one and a line to the right of one. And at one, we have the point 1, 2. But is it continuous there? No. What's the general limit at 1? The limit from the left and right of 1 you can use by direct substitution is 4. And the function value at 1 is 2. Does 4 equal 2? No. So what type of discontinuity have we? Is that a jump? It's a hole, right? Because the limit from the left and the right is going to be 4, but the function value is 2. Yeah. Remember, if it's not equals, you don't have to do the left and right side of the limit separately because it's the same function from both sides. You can just use direct substitution. So we know we have a hole there. Well, let's just actually sketch it, okay? Do a little bit better than just what we did up above there to get an idea. We'll go to 1, and this is 4. We'll put a 2 here, solid dot, open circle. And now we know the line has a slope of 1. It has a y-intercept of 3. So I'll just come in right there. We'll call that 3 if you want. And then it does that. That's what the function looks like. Does this function, which is defined everywhere, is it continuous everywhere? Obviously, no. So we can't use the first derivative test, but we have the graph. Do we have any critical values? We do, right? Where's the critical value? At 1. X equals 1 is the critical value. It's also the location of the hole, right? Now, if that dot were not there and it were just x plus 3 when x is at 1, then it would not be in the domain. That would not be a critical value. It would be an important value. It's a discontinuity, but the function is not defined there. So whenever it's not continuous, you can't do the first derivative test, okay? Because notice, what's the value of the derivative to the left? Immediately to the left, it's 1. And what's the value of the derivative immediately to the right? 1. Positive to the left, positive to the right. Did the sign of the slope change? Nope. But nonetheless, we still have a what there? Yeah, local min. Because when you go to the function value, immediately to the left, you have values that are bigger, and immediately to the right, you have values that are bigger. That is the ultimate litmus test for local minimums, okay? It just so happens if it's a continuous function, we could do it analytically with the first derivative test. So yes, you wouldn't really have to justify with the first derivative test, but you would say f has a local min, and did it say define the relative extrema? Okay, the local minimum of y equals 2 at x equals 1, comma, because now immediately is a big word to write. Immediately to the left, immediately to the right. So you could say because f of x is greater than 2 on, what's that magical word that means local? Either, yeah, side of x equals 1. That's probably the best way to justify it. Bless you. So I've said what the y value is there, and then immediately on either side, or on either side, the function value f of x is bigger than that number on either side. So that's not the first derivative test. We didn't say anything about the derivative there. Okay. All right. So if it's not continuous, you can still do it if you can sketch the graph. All right. And if you're at this level, if you're expected to answer that and it's not continuous, then it'll be something that should be graphable. Is that a word? Graphable? Yeah. Yeah. Graphable. All right. Now, everything that we've looked at so far has been defined at a point. But what if it's not defined there? If a function is not defined at a single x value, can that x value be a critical value? No. Therefore, can it be a local max, local min location? No. But is it still an important value? Yes. So it's important, and perhaps maybe outside of math class, some might argue it's critical, but in terms of what the definition of a critical value is, it's not. Okay, so we'll call it an important value. So values that make it into the number line chart, values to put into a first derivative f prime number line chart. Colon, I guess. 1, of course, CVs. Yeah, and number 2, any discontinuity. Any discontinuity. If the function's defined there, then it's going to be a critical value. If it's not defined there, then it's going to be an important value, right? So you can just say discons.
But you still need to see what's happening.
Right, because you can have, as you'll see, a vertical asymptote. And remember, a function can be increasing on one side and decreasing on the other. But you wouldn't call that the location of a local maximum, even though the derivative changes from positive to negative. Okay. And so of the example 8, the last one, I'm going to work example B. So a question like this showed up similarly on a free response question years and years and years ago. And there was a lot of people did not consider the discontinuity, and they lost bukus of points. All right. So we're trying to find the intervals of decreasing, increasing, and the x coordinates of the relative or local extrema again. So step 1, find the domain. It's in a nice quotient form. If you wanted to, you could split this up, right? Just be careful with the negative at front. But again, for domain purposes, if it's not piecewise, we're trying to avoid division by 0. We're trying to avoid taking square roots or fourth roots of negatives, and we can only take logs of positives. I don't see a radical, and I don't see any logs, but I see a denominator. Now I know right away that x can't be what? 0. Okay, x can't be 0. It's not in the domain. Now, is it a whole or a vertical asymptote? It's only a whole if it's removable. Or if you remember, if you plug in, the easiest way without factoring it is 0 over 0 when you plug in, that's the whole. Non-zero over 0 means VA, because non-zero over 0 is infinity. What do you get when you plug a 0 into the top? 1. Or 0 plus 1, which is 1. 1 divided by 0 is indicative of a vertical asymptote. So it is infinite. It's a VA. There's a VA at x equals 0. Okay. So is 0 a critical value? No, but is it important? Yes. Will he be in my number line chart? Yes, he's already there. He's waiting. Now, the question is, are there any critical values as well? So we need to take the derivative. And here's where you have the option if you want to like split it up and then take the derivative using the power rule after a little bit of rewriting, just so that you can get it back into a single fraction again. Or what I would probably do is just Hody high it. Because remember, when you Hody high something, it stays as a single term. All right. Now that negative out front, just because where it's at, it's kind of precarious. You can either distribute it through to both terms in the top. You can put it in front of the single term x squared in the bottom. Or what I'm going to do is I'm just going to block it off and put it out front and say it's a constant multiple, -1 times something. When I take the derivative, constant multiples go along for the ride. I think that's the easiest way. So f prime of x equals, well, let's just let -1 be right there. There he is. And then I can just Hody high the nice positive things on the inside. Huh? Hody high, Hody high. So ho, and then d high is 4x cubed. Hody high minus high, in parentheses, d ho is 2x. All over ho ho, that's x to the 4th. So see, it's already still preserved in single format. All right, now we got to simplify, simplify, simplify. Still got a -1 out front times, I get a 4x to the 5th. And if I distribute, this is where it gets a little bit tricky, right? If I were to distribute, you got to be careful. I'm distributing a 2x from the right-hand side, but I'm also distributing a -1 from the left-hand side. And some people sometimes mess that up. So if you'd rather just tell yourself I'm distributing a negative 2x, right? Or do it one at a time, I'll just distribute a negative 2x. I get a minus 2x to the 5th, and then a minus 2x. And then it's all over x to the 4th. All right, so I'm keeping now that negative on the same level as division bar. I get 2x to the 5th minus 2x over x to the 4th. Now I could stop here, split it up into my two sets of analyses and get the right answers, but there's still something I can do. Y'all see that? I can factor out an x, right? I can factor the x out of the top, and one of them will divide out in the bottom. So if I just get rid of one of the x's, I end up with 2x to the 4th. I can factor out a 2 as well from the top, but I get 2x to the 4th minus a 2 all over x cubed. So I didn't show the factoring out and dividing out. Now you don't have to do that, but getting rid of that x over x, which did cause a 0 over 0, which is not a whole, because we're still left with non-zero over 0. It's just an extra x that showed up, okay? And now if you want to factor out the 2, now since I'm factoring out a 2, I can put that in the numerator, and I'm left with x to the 4th minus 1 all over x cubed. So I think that's probably the best looking final version of our derivative. That's a good looking version of prime. X to the 4th minus 1, by the way, can be factored a lot more. It's a difference of 2 squares. It factors into x squared minus 1, x squared plus 1. And then, x squared minus 1 factors into x minus 1, x plus 1. But you know what? When you have something that simple, you don't really need to continue factoring it, because it's about, can you find the roots easily? And if you plugged in, can you figure the sign easily? And I think it's probably easier like that than with all those factors. So now we'll go down, since we have a quotient, f prime equals dne when the denominator equals 0. Well, that's when x equals 0. So if you're thorough in finding the values where the derivative is undefined, you might think that x equals 0 is a critical value. But since we are also thorough in finding the domain and having already identified that guy as not being a critical value, we're not going to make the mistake of thinking he's a critical value, right? So anytime you have a value that's a singularity, but it's not in the domain, like a vertical asymptote, he's going to try and sneak into club critical value, right? Because if the function's not defined there, neither will the derivative. Don't let him in. You're the bouncer at the door. So now we'll just say f prime equals 0 when the numerator equals 0. And now we'll divide by 2, and you could say x to the 4th equals 1. And now when I take the 4th root of both sides, do I need to consider plus or minus? Yes, anytime you're taking an eventh root. So it will be plus or minus 1. So students had a problem almost identical to this. A lot of students overlooked 0 because they were not thorough in finding where the derivative was undefined, nor were they thorough in finding the domain. And then a lot of students only got positive 1 because they didn't do plus or minus. So there was a lot of problems student-wise with this one. But we have 2 critical values and 1 important value. And now we can make a number line chart. Okay. And even though the function's not continuous for all real numbers, it's okay. We can use the first derivative test on continuous intervals within discontinuous functions. I should probably state that as well. The function, it's not an all or nothing thing. You don't have to throw the baby out with the bathwater, right? You can keep the bathwater, just throw out the baby. Wait, the other way around. Sorry. Yeah. All right, so we have critical value of -1. We have critical value of +1. If you ever have an important value that is not in the domain, it's going to be in the chart. Put it in there as a dotted line, not as a solid line. Why? Yeah, it's a reminder to yourself that it's a VA and therefore will not be a local max or min. All right, now we pick our values like -2, +2, -0.5, +0.5. Now, do we have a full-fledged factored version? Yeah, we have it right here, that yellow one. It's not fully factored, but it's factored well enough. So we plug in a -2. Now, notice the 2 out front is negative. I took it out from in front because it can be overlooked in the front. So when I plug in a -2, I get a positive times the -2 makes it negative, divided by, and then the bottom, like cube root, a negative cubed is negative and a positive cubed is positive. So I end up with a negative in the top and a negative in the bottom. Negative over negative is positive. Yeah. If you plug in a -1/2, now this one's interesting. -1/2 to the 4th is +1/16. And 1/16 positive minus 1 is negative, right? The negative times the -2 makes it positive in the top, and a negative cubed is negative in the bottom. So it's a positive divided by a negative. Negative, yeah. Plugging in a positive 1/2. 1/2 to the 4th is still 1/16. 1/16 minus 1 is negative, times the -2 makes it positive in the top, and then 1/2 cubed is positive in the bottom. Positive over positive is positive. And then when I plug in a 2 in the top, I get a positive times -2, which is negative, over positive cubed is positive. So negative over positive is negative. Okay. And there's the result. So again, from here, we can list the open intervals where the function's increasing or decreasing, no problem. But we can also do the local extrema. Local max there. Local max there. Is this a local min? F prime goes from negative to positive? No, it's not, because there's a vertical asymptote there. So really this function only has 2 local extrema. All right. So we would say then, and you can group these together. F has, yeah, that's good, Mason. F has local maxes at, and it said the X value at X equals, we could say plus or minus 1. You can group them together because they're both maximums, since F prime changes from positive to negative at X equals plus or minus 1. And that's it. Oh, okay. Let's just talk about that because that's a lot of writing. F is increasing. Thank you though. F is increasing from -infinity up to -1 parentheses, right? The open interval union parentheses 0 to 1 parentheses. And if you had to justify, since F prime is greater than 0 on these intervals, and F is decreasing from parentheses -1 to 0 parentheses union 1 to infinity parentheses on both, since F prime is negative or less than 0 on these intervals, right? So the number line chart for F prime gives you the ability to organize information that helps you answer all those questions so much more effortlessly and successfully. Yeah.
Did you say F has neither?
If it did, well, yeah, well, even if it did say at each critical value, determine if F has a local maximum or neither, we wouldn't need to address it because it's not even a critical value. Yeah.
I think you said this earlier, but whenever you're saying that, like from -infinity to -1, if you put that -1 in a bracket, would it be wrong?
Yeah, you could. No, you can. You can. Let me talk about why I'm glad you brought that up, because increasing from -infinity to -1 or -infinity to -1. Okay. It has to do with people's different version of what it means to be increasing and decreasing. So if you look at a hill like this, if you say a function is increasing up to that point, then you'd have to say it's decreasing from that point and to the right. Okay. And now some people like me have a problem with that, because I don't want to, there's a sharing violation. Now I'm saying at the high point, the function is both increasing and decreasing. And I don't like that. But people who accept that are like, well, that's what happens when two equally opposing forces ram heads, right? They nullify each other. So because it's both increasing and decreasing at that point, it's doing neither. And I'm like, okay, you can have that opinion. That's fine. I like to just say at that point, it's neither increasing nor decreasing. You can justify why however you want. And so I'm going to say it's increasing up to, but not at that point. So, I mean, that's really what it comes down to. Neither one is wrong. It's just kind of a philosophical kind of thing. It's one of the few things in math that's subjective. So I typically like to just say list the open intervals, but College Board, they're kind of iffy, Sometimes as a multiple choice question, they would only have this. You're not going to see an answer choice that's multiple choice where it has this and that, or one of them's right and one of them's wrong if it asks for increasing, decreasing. So yeah. All right. Now, if I were to comment here then on what happened that year, for the student that forgot to even consider zero, they lost an automatic point for not considering zero. And this was back in the day when they were still grading number line charts. So they knew you weren't considering zero when you didn't have any number line chart. But there was an additional penalty, right? There's typically the spirit of no double penalizations. Well, let's say that you didn't have zero in your number line chart. Now you're going to pick a number between -1 and 1. And the most common one you'd pick is 0. And then if you try to plug 0 back into the full-fledged factor of the derivative, you're going to get positive over 0. And you're like, positive over 0? Well, I don't even know what that is. It might be positive, right? Or that person's going to realize, well, positive over under 0, that doesn't make any sense. So then they might choose a different number. Well, that doesn't work for some weird reason. I'm not making the connection, but oh, well, let's choose a half. And then they get a negative. Now what's going to happen on that last interval? Are they going to see a sign change? Or I'm sorry, they would get, they'd get a negative, right? Oh, they get a positive. Yeah. So they wouldn't get this one here. They'd be like, oh, there's no sign change there. And they'd only get one of the two local extrema. And so then they lost another point for only listing one local max or min, or vice versa. If you found -1/2, you would only get the one on the left and not the right. So it was a double penalty, one for not considering 0, which then ultimately led to you missing a critical value or local maximum. So anyway, just be mindful of that. We always find the domain first, right? It's like walking up to somebody and introducing yourself, right? You don't just start judging them right out of the box, right? Or differentiating them without, introducing yourself.
That's right.
Jump in and take the derivative. No, but I barely know you, right? Finding the domain. Can't have that. All right. So the last one here, example 9. I briefly talked about this when we did the calculator application. See if you can answer this on your own. This makes a really splendid, quick, fast, easy, no calculator, multiple choice question. But we'll treat it as a short answer, open answer here. See what you get. See what you get. All right. Yeah. So reading carefully, it says if P prime equals this, how many local extrema, that's plural, local max or mins, does P have? If it said how many local extrema does P prime have, then we'd have to take the derivative of P prime to get its derivative. And that would be bleh, a triple product rule with some chains going on. But all we need to realize is, okay, P is going to have local max or mins at its critical values. That's where its derivative is 0 or undefined. Hey, there is its factored version of its derivative, which is a factored polynomial. So it's never undefined. It has how many critical values? Good. P has 3 critical values. Now that might be a question, right? If this were a multiple choice, sometimes it's that easy. How many values, critical values does P have? As long as you realize that you're given the derivative in factored form. And they happen to be 5, -6, and 7, right? For what it's worth, 5, -6, and 7. For those of you who actually did the number line chart, I'm not going to do the number line chart. But what you should notice is every time you plugged in, the middle factor gave you a positive term, right? So I mentioned this the other day, the exponents on the two factors that are odd, okay? If you have a odd exponent, you are going to see a sign change at that critical value. Because if you were to look at that graph by itself, x minus 5 cubed, here's 5, it's going to do this and do that, right? You're going to see a sign change. It's going to cross the x-axis. Same thing, x minus 7. Over here at 7, it's going to cross. It's going to change signs. But what will the graph look like of x plus 6 squared? Well, here's -6, and it's going to go boing, and you're not going to see a sign change there. Well, that translates into the product of those sign changes. So of the three critical values, since this one here is an even, and the only one that's even exponent, it's the only one that will not see a sign change. The others, the 1 and the 3, will see a sign change. So of the three critical values, P has 2 local extrema. Okay, and that's question is designed to be done that quickly. If you look at your number line chart that you completed, you should notice that there is no sign change immediately to the left and right of at -6, but there is on the other two. Now, if you wanted to know whether x equals 5 was a local max or min, you'd actually have to do the number line chart. Okay, because when we say local extrema, we mean max or min. We don't care for plural how the sign changes. But if you just want to know local maximums, then you'd have to do the quick number line chart and see. All right. But this question can be done very quickly. All right. Very similar to what we did the other day when we graphed it, and you saw it crossing and bouncing and crossing again. That one had symmetry. This one doesn't have symmetry because we have a cubic and a linear, and the roots are not symmetrical, but it's the same idea. Okay, so we're going to start 3.4 on Monday. There's how much time? We got a little bit of time left here. So make sure you understand the first derivative. Make sure you understand the first derivative test, what it's a test for, how to use it, the importance of a number line chart, discontinuities, critical values, all that good stuff. Right now, let's just kind of let's just review some stuff. What is the derivative with respect to x of arc sine of e to the 2x? Okay, just you can do it at the bottom of your notes. Yeah, and then when we're done, you can submit your notes for 3.3. Good question. I'll just give you a little bit of time to don't simplify. Just take the derivative and we'll go over it. Does anyone remember the derivative of arc sine? Oh, we all do. I'm sorry. Silly question. Now would be a good time to do that memorization test that Skirhawk gave before, because we've had 2 weeks to let it gel over the Christmas break. And by gel, I mean turn to jelly. What's that? No, just like in the near future, like maybe next week. No, we can talk about it on Monday when everyone's back and say, let's see, 7, 8, 9, 10, 11. The Wednesday would be the 12th. That's an even day. So maybe like next Wednesday, a memorization test. And that can be our first test of the 9 weeks. In fact, while y'all are doing this, let me just write that down. Wednesday, yeah, 1, 12, 22, memorization test. Oh, okay. Yeah. Well, I'll record the lesson next Friday, and I'll be sure to say hi, Ellery. So when you're listening to it, you'll feel like you were here. Yeah. But it'll be through any memorization that we've gone up through 3.3. Okay. Like every derivative rule, like trig might be on there, like what's cosecant of 5 pi thirds, It'll just be you writing it down. Like I'll give you the left side, you give me the right side. Or like, what's the formula for the volume of a sphere?
Basically all the box that they describe.
Yeah, every box. Yeah.
50 questions, 15 minutes rapid fire. It better be memorized. I can see questions. Because half of it already is.
I wouldn't put one like this because this is a combination of skills. But I might do this. What's the derivative with respect to x of arc sine of x? And you would be like, oh, it's 1 over the square root of 1 minus x squared. Boom. Or I might say, what's the derivative with respect to x of e to the x? And you'd be, oh, e to the x, more please, like that, right? Or the derivative with respect to x of 2 to the x. You'd be like, oh, 2 to the x times the natural log of 2. Yeah. Or what's the derivative with respect to x of log base 2 of x? Oh, it's 1 over x with the natural log of 2 in the denominator. Oh, and what if the absolute values were there? Oh, same, right, good. That kind of stuff, et cetera, et cetera. I hope so. Yeah. Right. Miss them all, make a 70, not a bad deal. BC curve. No, it'd be a test grade. It'd be a test grade. Major grade. Yeah, y'all are more likely to prepare better. Y'all prepare better if it's test grade. Plus, we need test grades anyway. We need to generate test grades. All right, so this is chain rule, right? E, arc sine is on the outside, E is on the inside, and 2x is the innermost. So 3 layers, 3 factors, right? Work from the outside in. This is the verb format as well, right? So ddx of the ddx goes away. So it's just going to be 1 over the square root of 1 minus the blob squared. If this were just x, that would just be x, but it's not. It's e to the 2x. And then times, we go into the next layer and we see e to the blob. The derivative of e to the blob is e to the blob times the natural log of e, which we don't need. And then times the derivative of the innermost blob, 2. And there's the answer. Unsimplified. Simplified, it's 2e to the dos equis. Too early for that, sorry. 1 minus e to the, what is 2x quantity, e to the 2x quantity squared? E to the 4x, good. When you raise a power to power, you multiply. It's not 2x squared, it's not 4x squared, it's just 4x. Okay? Yeah, okay, all right. How about this one? What if f is equal to cosecant squared of 5x squared minus tangent of x, f prime equals what? Yeah. So this is the noun format now. I've defined the expression. Yeah. Don't miss a layer. Don't miss a layer. You don't love it that much? I do love it. Oh, you would marry it? I would marry it. Oh, you would. Okay.
Horseback with chain rule? What? Well, we go horseback riding together. Mason. The chain rule?
No. No. And again, you wouldn't have this question on the memorization test because this is an application of several rules. But this is a good way to review all the individual rules. You have to put the 2 up there or you're going to miss a layer. Yes, 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 yes. Don't miss a layer. Don't miss a layer.
It's like, I think the chain rule is one. She's so deep. She's so developed. The chain rule. It's just. I'm so sorry. I call it chain rule, but I said it's like. Wait a minute.
There it is if you want to compare. 2 blob to the first, rewrite the blob, and then the derivative of cosecant, as is anything that has a co in it, whether it's inverse or arc co or just co, it's negative something. And you don't put dot negative, do you? Grrr. You put dot parenthesis negative, and then it's cosecant, cotangent of the same blob. And then finally, the derivative of the last blob, 10x minus, and then the derivative of tangent is secant squared. And that's it. Almost right. Almost right. All right. How about this one? Y equals x to the x. Y prime equals what? Not on the AP exam. Will be on my exam. Geez, Luis. Jiminy crickets. Ay, Pinocchio. Hey, hey. Yeah, yeah.
I'm gonna start singing the natural log on the side.
You just need to you're a player. If you wed everything you see, then you have to become polygamous.
I would be Mormon.
Perhaps.
That would be crazy.
Is that a reason to become Mormon?
No.
Simply for the polygamy?
I don't think I could give up coffee.
Oh, I didn't realize that. I'm out too then.
If I don't drink coffee, I sleep through this class.
I wouldn't mind just living in freaking Utah. It's beautiful there.
Utah's great. Utah's great.
Going to the Salt Lake City Cathedral and listening to the beautiful organ and the boys choir singing, walking across the lake. Well, let's see. Let's finish this real quick. You have to take the log of both sides. Natural log of y equals the natural log of x to the x. Because it brings it to the front. X times the natural log of x. Now you take the derivative implicitly, so you need to put d dx. The left side becomes 1 over y times dy dx. And this side is a product rule. 1 times ln of x plus x times 1 over x. And then the last thing we need to do is solve for dy dx by multiplying both sides by y. And so we get natural log of x plus 1 if you simplify this, and then times y. But remember, y was originally x to the x. So there it is. That's called logarithmic differentiation. That's when there is no log in the original expression or function, but because it's a variable raised to a variable power, it's not a power rule, it's not exponential. You have to take the log of both sides to bring it back on the ground floor. But then you turn it into an implicit problem, so you have to solve for dy dx at the end. All right. Okay. All right. 3.4, we'll start it on Monday. We will test on Wednesday over memorization and everything. And that includes the unit circle. That includes your identities like cosine squared plus sine squared. Oh, that's Wednesday. Watch. Go to Calculus Maximus. If you look at the top, it says pre-calculus stuff to know cold. If you go there, those are your trig identities that you need to know through the double angles. Yeah, you don't need to know the power reducing. All right, but sine of 2x, cosine of 2x. Those are the ones you need to know. Yeah, it's on the website, but you don't need to know these. Yep. He has no time for the website. He's too busy in his polyamorous relationships.